Have you ever wondered why a little bit of heat can make things happen so much faster? Like cooking an egg or lighting a match. It seems obvious, right? Heat makes things go. But why? Why does a tiny change in temperature have such a massive, outsized effect on the speed of chemical reactions? Well, the answer is way more interesting than you might think, and honestly, a little counterintuitive. So let's get into it.
All right, here's our game plan. We're going to start by figuring out why reactions need a push in the first place. Then, we'll uncover the real reason heat is so powerful. That's going to lead us to something called the activation energy barrier. We'll even decode the famous Arrhenius equation that ties it all together. And finally, we'll look at a clever trick for making reactions faster.
Okay, first up, why do reactions need a push to get started? I mean, if you mix the right ingredients, shouldn't they just go? I want you to think about this for a second. That piece of paper on your desk, or maybe a book on your shelf, it's made of flammable stuff, and it's literally sitting in a bath of oxygen, the exact thing it needs to burn. All the ingredients are right there. So why isn't it on fire? Clearly something's missing. There's some kind of secret handshake that has to happen at the molecular level for the reaction to actually kick off.
And that brings us to a really core idea in chemistry called collision theory. It starts off simple enough. Rule number 1. For a chemical reaction to happen, the molecules have to physically bump into each other. Makes sense. But, and this is the big one, just bumping into each other isn't enough. The collision has to be effective.
So what does an effective collision look like? Well, this image breaks it down perfectly. You need two things to happen at the exact same time. First, the molecules have to smash into each other with enough energy. They need to be moving fast enough to actually break old bonds. A gentle little tap won't cut it. And second, they have to hit each other in just the right orientation, like two puzzle pieces clicking into place. If they're lined up wrong, like you see in that ineffective collision example, they just bounce off each other, no reaction, no exceptions. It's about having enough energy and the right geometry.
Okay, so if collisions need energy, that's where heat comes in, right? Common sense says when you heat things up, molecules move faster, so they collide more often. Problem solved. Well, let's see if that's actually true. This is what we all intuitively think. You add heat, particles start zipping around like crazy, they bang into each other more and more, and boom, the reaction speeds up. It seems so logical. But it's not the whole story. It's not even the most important part of the story. Because when you actually run the numbers, you find something really surprising. Let's say you take a typical gas and raise its temperature by 10 degrees Celsius, not a huge amount. The number of collisions, the frequency, only goes up by about 1.7%. That's it. Barely a noticeable bump. But, and this is the whole mystery right here, that same modest 10-degree temperature increase doesn't just bump the reaction rate by 1.7%. No way. It often doubles or even triples it. That's a 100% to 200% increase. So how on earth does a tiny 1.7% increase in collisions lead to a massive 200% increase in speed? The math just doesn't add up. This is the big puzzle. Our simple idea that more collisions means a faster reaction is clearly wrong. Heat is doing something else, something far more powerful that's supercharging the reaction. So what is this secret ingredient? The answer to this puzzle has a name: the activation energy barrier. The best way to think about it is like a giant hill that every single molecule has to climb before it's allowed to react. Officially, activation energy is the minimum amount of energy you need to get a reaction started. It's the entry fee. I love the analogy of pushing a giant boulder over a hill. You can nudge it all day long and nothing's going to happen. You have to give it one big, sustained push. You have to invest a lot of energy, the activation energy, just to get it to the very top of the hill. Once it's there, sure, it can roll down the other side all on its own. So how does this energy hill connect back to temperature? Well, the key is that in any group of molecules, not all of them have the same energy. It's a whole distribution, which we can see in this graph called a Maxwell-Boltzmann distribution. Don't worry about the name, just look at the shape. Most of the molecules are clumped right here around the average energy. But you've got some slowpokes on the left, and way over on the right, you have a few super high-energy speed demons. Now let's put our activation energy hill on this graph. We'll draw a line right here. This line represents the minimum energy required to react. And you can see it immediately. The vast majority of molecules, all this stuff to the left of the line, they just don't have enough juice to make it over the hill. Only this tiny, shaded sliver of molecules, way out in the high-energy tail, have what it takes to actually react. And here it is. This is the big aha moment. This is the secret. When you raise the temperature, the whole curve shifts a little bit to the right, but it also flattens out and gets broader. And look what happens way over here in the high-energy tail. The number of molecules that now have enough energy to clear that activation barrier gets way bigger. That shaded area might easily double or triple in size. So that's the answer. It's not that we're getting slightly more collisions, it's that we are getting a huge increase in the number of effective, high-energy collisions.
This whole beautiful relationship between temperature and the number of effective collisions wasn't just a nice idea. It was actually captured perfectly in a really elegant piece of math. So let me introduce you to the Arrhenius equation. Now, I know equations can look a little intimidating, but stick with me, because this is basically the story we've just told, but in mathematical language. It was figured out way back in 1889, and it beautifully connects the reaction rate, K, with that energy hill, EA, and the temperature, T. Let's just break it down real quick. So K is just the speed of our reaction. A is a number that basically accounts for how often molecules collide in the right orientation. EA is our energy hill. R is just a constant you could ignore for now, and T is the temperature. The magic is all in that exponent. See how temperature T is in the denominator? That means when you make T just a little bit bigger, that whole negative exponent gets a lot closer to 0. And because of how exponents work, that makes the E term shoot up exponentially. And that's why our reaction rate, K, just explodes. It's the math behind our aha moment. And this is not just some dusty old theory. Chemists use this every single day. The really clever part is that they can rearrange the equation so that if they plot their experimental data, the reaction rate at different temperatures, they get a perfect straight line. And the slope of that line tells them the exact height of the activation energy hill for that specific reaction. It's an incredibly powerful tool for understanding and controlling chemistry. So we know we can make reactions faster by adding heat to get more molecules over that energy hill. But it begs the question, is there another way? What if, instead of pushing more molecules over the hill, we could just lower the hill itself? Well, that is exactly what a catalyst does. Take a look at this diagram. The normal reaction has to climb this really high energy hill, EA. What a catalyst does is it creates a totally different path for the reaction to take, a shortcut with a much, much lower activation energy, which we call ECAT. By lowering that barrier, a much bigger percentage of the molecules already have enough energy to make it over. And just like that, the reaction rate goes through the roof, all without even touching the temperature. Now, this whole energy hill idea we've been using, which comes from collision theory, is an amazing and powerful model. But of course, science is always digging deeper. A more modern idea called transition state theory actually zooms in on what's happening at the very peak of that hill. It talks about this weird, unstable intermediate state called an activated complex. It's a more detailed view that helps explain more complicated reactions, but it's built right on top of the foundation we just talked about. So when you think about it, everything from how we digest our food to how we manufacture plastics to the biochemistry inside our own cells, the speed of all of it is controlled by these tiny invisible energy barriers. It really makes you wonder, doesn't it? What amazing breakthroughs, new medicines, new sustainable materials, new sources of clean energy are just sitting there waiting for us, locked behind the next energy barrier that we've learned how to lower. Thanks for watching.